Section 4.2 is really talking about polynomial functions and the graphs of polynomial functions. And there's a bunch of terminology we need to get down before we start talking or graphing any of these functions. First, a definition of a polynomial. Well, it's a non-negative integer and it has different terms to it. And as you can see in this example, we might have a coefficient to each term, and each term might have a variable with an exponent. And these exponents they recognize, they call them n's, and the leading term has is called the leading coefficient in front of it. In other words, the variable, what's multiplied times the variable would be the leading coefficient of that term. So how do you look at a polynomial function with 2 degrees or higher? Well, it's a smooth, continuous line that you would draw without lifting your pen or pencil from the paper. That would be kind of how we look at it. It has curves, it has turns, and depending on this exponent and this leading coefficient here, we can tell a lot about it without even graphing it. We can tell how many turns it's going to make from certain things like the factors of it. So we've got a lot of work to do with these polynomial functions. First, we're going to look at one here that's called g of x. And it says let g of x is equal to 2x cubed minus 6x squared minus 32x plus 96. Now, the important thing to note is that our function always has to be written from the greatest exponent down to the smallest. If it isn't written in this format, this one is, then that's the first step, is to put it in descending order from the highest exponent, the term with the highest exponent, down to the constant term, or the term that doesn't have any exponent, it doesn't have any variables at all. And then it asked questions. What's the degree of the polynomial? The question is, what is the exponent for the highest degree? In other words, what is the biggest exponent in each of our terms? Well, it should be this one in the first term. And so this is a polynomial of degree 3. What is the constant term? Well, now the constant term is the number that doesn't have a variable at the end. And so we will say the constant term is 96 for this particular problem. And then it says, what is the leading coefficient? Well, the leading coefficient is the number that's multiplied in front, the coefficient of the leading term. So it's going to be the coefficient of the one with the largest exponent. In this case, it's going to be the number 2. And then what is the leading term? Well, this is the entire term would be the leading term. So we'd say that's a positive 2x cubed. Now, the rest of it is important, but those are really important features for us to pick out of every polynomial function that we find. So let's look at a couple of them and see if we can pick this out. The first one says we need to find the degree, the leading coefficient, and rewrite it in descending powers of x if we have to. So first of all, I look at it and it is definitely not in the right order, so I'm going to rewrite it in descending powers of x. I'll start with x cubed, the x cubed term. And then the next one is going to be this x squared. It's a positive 10x squared. The next one would be my x term, and it's a negative 3x. And the final one is just the constant term. It is a negative 7. So what is the degree of this polynomial? Well, the degree is the exponent, or the degree of the leading term. So this is going to be a degree 3. And then what is the leading coefficient? I'm going to call that, well, I'll just call it the leading coefficient. The leading coefficient of this one is going to be 5. Now, it's important to note certain things about these. We want to note that this degree is an odd degree. We want to note that this leading coefficient is positive, but we'll talk about that in just a minute. But those are the reasons we have to identify them. We can tell a lot about our graph just from that leading coefficient and that leading degree, the highest degree. Okay, let's take a look at the second one. It starts with x to the 5th, x to the 4th, x cubed, x squared, x and 10. And look, some of these terms have zeros in them, don't they? Coefficients of 0, but that's okay. All we want is the degree, which is the leading term. It's the exponent of the leading term would be 5. So this one's to the 5th degree, we would say. And what is the leading coefficient? Well, the leading coefficient for this one is going to be a positive 4. Now, the next one is a little odd, and I just want you to recognize this. This has a square root of x. So what would the exponent be of the square root of x? Well, it's not really going to be a whole number at all. It's not an integer. And that's one of the requirements for our polynomial functions. So when I say this is 3x to the power of 1/2, isn't it? It takes it away from being our polynomial function, and I can just say this one doesn't work for me. On this page, I want to give you a lot of information in a chart or a graph, if you will, at the top that talks about the leading coefficient test. And when we finish this page, I want you to make your own abbreviated chart that you can carry with you and have with you when you're doing the homework. First, it's telling us as x increases or decreases without bound, the graph of the polynomial function will either rise or falls, depending on how many variables that we have, of what the value of that exponent is. It's going to also depend on the leading coefficient. So those two things we need to know. We need to know what's the degree and what is that leading coefficient. So what we look at first is, what if it has an odd degree? Now this is the degree. When it says n, we're talking about the degree. What if the degree of the polynomial is odd? In other words, it would be like a 3 or even or 5 or something like that. Well, that tells us that then we check the leading coefficient, and we can do one of two things. If the leading coefficient is positive, then what the graph is going to do is it's going to fall to the left and it's going to rise to the right. In other words, I like to think about it as if the graph is, the leading coefficient is positive, then the end behavior of that graph is going to be positive, in a positive direction. It's going to go like uphill. So this is kind of what it would look like if it was an odd degree. It might, more likely, it would have more turns than this, but even if it was to the degree 3, we would say it had a rise, a fall, and a rise. Well, that's 3 different turns or 3 different directions, and that's kind of what we think about is going to happen with a graph that has an exponent of 3, or the 3 is the highest degree. Now, what if that leading coefficient, however, is negative? Well, then the same thing I told you is going to happen. The end behavior of the graph is going to go in a negative direction, right? The end behavior of the graph is going to go in a negative direction. Now, the other thing that you have to think about with these graphs is that since it is an odd degree, these directions are opposites, aren't they? The direction of them is always opposite. If I know what the end behavior is going to be, because I know it has a positive leading coefficient, and I know it has an odd degree, I know these have to be opposite, so I know that the first one has to go the opposite of up, the first one has to go the opposite of down for this one. And that's kind of how you might be able to help memorize this particular behavior of your graphs. Give me just a second, because I do want to focus this in for you a little bit better. Okay, so odd degree polynomial functions have graphs that have opposite behaviors at each end. That's what we expect from odd degrees, opposite behaviors. If it is a positive leading coefficient, we expect the end of the graph to go up. If it's a negative leading coefficient, we expect the end of the graph to go down. Now let's look at it when we have a degree that's even. Well, down here, as you can see, I've said, even degree polynomials have graphs with the same behavior at the end. Even degree, same behavior. Odd degree, opposite behavior at the end of the graph, okay? So what do we have with the end of the graph if the leading coefficient is positive? Well, the same thing. It goes up. End of the graph goes up. It's an even degree, though, so both of the beginning and the end are going to point up. So it's going to fall, rise, fall, and rise, perhaps. An even degree would expect 4 changes of behavior, or exactly, it would say 4 directions. Down, up, down, up. That would be degree 4, would be what we would expect of the graph. Let's look at the other side of it and say if the leading coefficient is negative, well, we're going to expect the end of our graph to go down. We know that if it has an even polynomial function, if it's even, then both of these ends have to do the exact same thing. So if the end went down, the beginning has to go down. So this one, let's say, had the same thing, and we would look at it to have an even number of directions. 1, 2, 3, 4, 5, and 6 is going to give us 6. So I would expect this one, this particular example, to be a degree 6, because that's kind of what our degrees are going to tell us, okay? All right, let's take a look at the examples at the bottom and see if we can put this to work. But before we do that, I want you to take that information and create a little leading coefficient test chart. This is talking about what is the end behavior on the graph going to do. Well, if it is an even degree, then I expect them both of them to do the same thing. So I'm going to write down here, I'm going to say they both have the same end behavior, don't they? If it's odd, I expect them to have opposite end behaviors. This is the ends of my graph, so the end behavior of my graph. If it is a positive leading coefficient, well, I expect the end behavior to be up every time when it's positive, right? If it is a negative leading coefficient, I expect the end of my graph to go down. So now I have to look at whether it's an even or odd function to say, what does the beginning of my graph look like? If it's even, they both do the same thing. So this one's going to be up, and this one's going to be down. If it's odd, they do opposite things. Since this one is up, the first one would be down. Since this one is down, the first one would be up. And you can draw them straight up and down if you want to. Usually they are sort of angled like this. So there's your leading coefficient test piece of paper that you need to have with you. It'll help you as we go through this. Let's take a look at a couple of problems down here. Let's take a look at this first function. It is degree. I mean, they've already been written in descending order. We want to determine the end of the graph just by looking at the leading coefficient. So we want the end behavior of our graph. So the first thing I'm going to say is this one has a degree of 3. Now, that's an odd degree, right? That's going to tell me that my tails of my graph are going to do opposite things. My directions are going to be opposite at the ends of my graph. But what is the leading coefficient? The leading coefficient for this one is a -5. That's a negative, which tells me that the end of my graph is going to go down, right? And since I know it's odd, I know the beginning of my graph has to do the opposite, so it's going to go up. Now, it's a degree 3, so what I'm really expecting to happen is it to have 3 different directions. It goes down, goes up, and it goes down again. That's probably what my graph is going to look like. Let's take a look at number 2, which we have to rewrite, don't we? We can't use it in this format. We've got to say f of x is equal to, let's write these in descending order. We start with the biggest exponent, and the next one we have is -4x squared, and the final one is +1. We don't need the missing exponents to be listed for us. That's all we really need for this. I want to pick out the degree by looking at that leading term and saying, well, it's a degree 5, isn't it? And what do I need to know about the degree? Well, I need to know if it's even or odd. And then I look at the leading coefficient, and I say there isn't a number in front of my first term, so that's a 1, isn't it? But it will be a positive 1. Now, I know that because it's positive, that they're going to both go in this, they're going to, the end of my graph is going to go up, right? I know that this positive leading coefficient, the end of my graph has to go up. But because it's odd, I know that these are going to do opposites, right? So the beginning of my graph is going to point in down direction like this. Now it has, and this is an interesting one, it has a degree of 5. So I'm expecting a behavior to be sort of a little bit different. I'm expecting it to have 5 directions. And no, it starts like this from the down position. So I go 1, 2, 3, 4, and 5 would give it the turn up it needs at the end. That's what I'm expecting it to look like. It could look a little different. It could just have actually 3 turns to it, and that would be okay. It just kind of works out a little bit differently in the math that we'll be working on later. And the next one has to be rewritten for us again. Let's say this time f of x is equal to, and we'll start with the highest term. The highest degree we've got is 2x to the power 4. And then I'm going to put the x cubed term next, and the x squared term. And there is an x term. And finally, I have just the plain constant term, 105. All right, so what do I know about this? The degree of this function is going to be 4, right? And I know that that's an even number. And then I look at the leading coefficient, and I say it's a 2. And a 2 is positive 2, right? So what do I expect? Well, because it's positive, what I'm expecting is that the end of the graph and the beginning of the graph are going to do the same thing. Because it is an even function, because it's positive, I'm expecting the end of the graph to go up. Because it's an even function, I'm expecting both of them to do the same thing. That's what I was trying to say. Okay, so this is what I'm looking at. And what I would do until you get used to this is go to your chart and ask yourself those questions. Look at your chart and figure out what your graph is doing. But make sure that you can actually memorize it, because you won't have your chart on your test, will you? All right, so what did we expect from this one? We have an x to the 4th. We have a degree of 4. I'm really expecting it to have 4 different directions it takes. I'm expecting it to start down 1, 2, 3, and kind of end going up like this. Now, I don't know what the graph looks like, but I do know the beginning and end of it have to point upwards, and I know it has a degree of 4, so that's a good guess. On the next page, page 10, we're really going to talk about using these zeros of polynomial functions to see if we can find out the directions that this function takes when it turns. And it's a really interesting thing that happens to it. We are looking at factoring these functions, which you've worked a lot on factoring functions before, factoring polynomials before. So we're going to look at factoring them, and then we're going to look at what degree those factors have to see what kind of multiplicity the zeros of the function have. So first of all, when you're talking about the zeros of the polynomial functions, you're talking about where it's going to cross the x-axis, or where it's going to touch the x-axis. So it's going to be really an x-intercept of the graph. And that x-intercept, of course, is going to be where y is equal to 0 for this graph, isn't it? And so we're going to be looking at the roots of the polynomial function, and we'll be calling them the zeros of f, or the zeros of the function. So what if we have one that has the same root that happens multiple times? In other words, what if we had an x minus 2 to the power of 5? So we knew, like it in the first example, this particular factor happened 5 times. Well, that means it has a multiplicity of 5. In this function, it's x minus 2 times x minus 2 times x, 5 times, really. So a multiplicity of 5 is interesting. If it has an even multiplicity, like a multiplicity of 2, if this was x minus 2 squared, then the graph actually at that point, whatever the 0 is, it touches the axis and it turns around. It also has a tendency to sort of flatten out near that 0. But when it has an odd multiplicity, the graph doesn't touch and turn, it crosses the x-axis at whatever that point is. So we're looking for these even and odd multiplicities when we are looking for the roots of the graph, or the zeros of the graph. So this one's already factored for us, so this is kind of easy for us to look at. Let's talk about it and see, what would the zeros of this graph be? Well, it would be where y is equal to 0, wouldn't it? So what is going to make this graph, which is this function, which is negative 3 times x minus 2 to the power of 5 times x minus 6, what would make this statement true? Now, all I'd have to do is say, well, negative 3, I've got 1, 0 is equal to negative 3 is one factor, isn't it? But we know 0 is never equal to negative 3, so we can say that's not going to help us. It is not a factor. It's not going to be one of our zeros. But what about this one? X minus 2 to the power of 5. Well, that's really x minus 2, and I can look at it and say, well, 0 would equal x minus 2. And when I solve, I say x is equal to a positive 2. And you can probably do that without writing it out by now. I know that one of my zeros is going to be where x is equal to a positive 2. And it's going to happen 5 times. I don't need to solve this equation 5 times to see that it's going to come out to be the same, x equals 2 each time. So I'm going to say one of my zeros is x is equal to 2, and it is repeated 5 times. So what do I say? I say it has a multiplicity of 5. Okay, multiplicity of 5. X equals 2 has a multiplicity of 5. Now let's look at another one. There's another factor in this graph that could cause us to have a 0 statement, and it would be 0 is equal to x minus 6. And if we solve this one, we find x is equal to a positive 6. So I say x would equal 6. And how many times is it repeated? 1 time. So it has a multiplicity of 1. All right, that tells me something, doesn't it? If it has an even multiplicity, it touches and turns. If it has an odd multiplicity, it crosses the graph at that point. Now, both of these, both 5 and 1, are odd multiplicities. So at both points, the graph crosses, and it crosses the x-axis at that point. That tells me a lot about my graph. Now, I already know that this graph is going to look something like it's going to have 5 directions in it. And I should be able to tell from the beginning, the coefficient, should be able to tell the end behavior of the graph. And let's look at the degree of this graph. Now, the degree of this graph is interesting because this is x to the power of 5, isn't it? And this is multiplied times x to the power of 1. I'm really only interested in the x's. There's no variable out here. But when I say x to the power of 5 times x to the power of 1, I add those exponents, and I would say it has a degree of 5 plus 1, which is 6. Remember, I'm only interested in the exponents of the variables, right? And the strongest, the highest variable, if it's already factored, would be what happens when I multiply those factors together, right? And I would end up with the highest variable being x to the 5th times x to the 1st multiplied together. It's going to give me x to the 6th degree of 6. And then I'm looking at what's the leading coefficient. Well, the leading coefficient has already been picked out of this graph for me. The leading coefficient of this graph is negative. So the degree is going to be even. The leading coefficient is going to be negative. And I would take my chart and make a decision about what the end behaviors of my graph are going to be. Now, I always start with the leading coefficient being negative. The leading coefficient being negative means that it's going to end in a downward direction. And then I look at the even and I say, well, if it's even, they're both going to do the same thing. So this is going to be the end behaviors of my graph. And I know it's going to have 5 different directions to it. I'm sorry, 6 different directions to it. So I can say it would probably go like this. It would go up. That's 1, 2, 3, 4, 5, 6. Something like that is what I'm expecting my function to look like. You can tell we can tell a lot about our functions just by doing these simple exercises. Let's take a look at this one and see what it does. Now this one I've got is written in the correct order, so I'm okay here, but it's not factored. So if I'm going to find the zeros of this graph, I have got to factor it. So I'm going to say, well, this is 4 terms, right? So we always factor 4 terms by grouping them. I'll take the first 2 and group them together. And then this one has a minus in front of it, so I'm going to add a plus sign and stick the minus in the second group. That helps me when I'm grouping. Go back to how you did this in 1033. And then I'm going to say, okay, I need to bring out my greatest common factor, which would be x squared. And what do I have left? Well, I have x minus 2. I'm going to bring out my greatest factor, which is going to be a negative 4 this time. And when I have that negative in the second group, I always factor out the negative. And that means it changes both of those signs. What do I have left? A positive x, and it's going to be a negative 2, because negative 4 times negative 2 gave me that positive 8. So I do have matching binomials. And what I have here is x squared minus 4 times x minus 2 times, that's it, right? X minus 2. I've got everything. I've got this matching binomial, and I've got everything else written as the first binomial. But then I realized that this is a difference of 2 squares, and I can factor it again. It factors into plus and minus signs, the square root of the first term, and the square root of the second term. And then I don't forget, I already had that x minus 2 factor. So my function is going to factor into x plus 2 times x minus 2 times x minus 2. And now I'm looking for the zeros of x. I'm looking for the zeros of the function. And I said, well, one of them is going to be if x plus 2 is equal to 0. I'll go ahead and set it like that. X plus 2 equals 0. And how would that work? Well, that would work. I would subtract 2 from both sides and say one of them is going to be when x is negative 2. The other one is going to be, another one is going to be when x minus 2 equals 0. I'll add 2 to both sides, and that would be when x is a positive 2. And that one happens twice. So this x minus 2, this positive 2 has a multiplicity, doesn't it, of 2. And this one only happened one time, so we would say it had a multiplicity of 1. What do we mean by, what does that do for us? Well, this one with an odd multiplicity means it's going to cross the graph at that point. With the even multiplicity, it's going to touch it, right? And turn around. So at this point, I'm going to cross the x-axis. I would expect it to cross the x-axis at x equals negative 2. And at x equals 2, I expect it to touch and turn. At x equals 2, positive 2. So that's kind of an interesting thought. And I'm going to see if I can do a kind of good job at drawing this one. But first, I really need to know what the end behaviors of my graph are going to be. So let me look at the end behaviors by looking at the degree. The degree of this graph is a 3, which is odd. The leading coefficient of this graph, if I look at this, of this function, is a 1, which is positive. Positive tells me that the end behavior of my graph will be going in an up direction. Odd tells me that the beginning is going to do something different from the end. So that's what I'm expecting to happen. You know, it's got a degree of 3, doesn't it? So I'm expecting it, I'll just draw it up here, I'm expecting it to start going up and then turn again. There's up direction, down direction, up direction. There's 3 different directions in this graph, I believe. So can I graph a little bit of it? Can I see what it's kind of going to look like here? Well, I need where x is negative 2. I'll put it over here. X is negative 2 there. And where x is a positive 2. I expect it to cross at this point, don't I? And I don't really know where it's crossing the y-axis. I haven't gotten into that yet. And at the x is equal to positive 2, I'm expecting it to touch and turn. Now, it really does flatten more than I've drawn it, but that's giving you an idea of what this graph is going to look like. Now, you can take your graphing calculator at this point, and you can enter this, if you want to, into y is equal to, and we'll look at this graph really quickly. I'm going to come over here, and I'm going to clear this one out, and I'm going to say I want my graph to be x cubed and I'm going to say minus 2x squared, and then I say minus 4x, and I say plus 8. And I'm looking at it thinking, okay, I've got an interesting looking graph. That's what it looks like. Let me just see what I've got. I don't remember what my window's set to, but let me see if it goes onto this graph. It looks like it's fitting fairly nicely on my graph, doesn't it? And doesn't it appear at x is equal to 2 and x is equal to negative 2 to cross and touch and turn and go back? If I wanted to know exactly those points, I would look at the table of my graph, remember. And if your graph is not, your window's not looking like this or not looking the same, remember you can set that in using the window button. You can go in and set what your increments of x and y you want them to be. On page 11, let's take and talk about this function in detail. And it's got a bunch of questions that you're going to be asked in your homework, some of them, and so I want to cover them all here. We're going to use the leading coefficient test to determine what the graph's end behavior is. We're going to find where it intercepts the x-axis. In other words, we're going to look for the zeros of x, aren't we? Those are the zeros of x. we're going to find the y-intercept, and of course, that's going to be where, x is equal to 0. And then we're going to determine whether it has y-axis symmetry, origin symmetry, or neither. So we'll get a chance to talk a little about that. And then we're going to try and graph this function. Now, this first one I'm going to give you is going to be a very difficult one for you to graph using your calculator because it's going to end up with decimals, not whole numbers, as points or fractions. So I kind of wanted to show you an example of that one, and that's why we're going to do this one first. The first thing I want you to notice is that from the previous section 4.1 that this graph is a parabola, right? It is the highest degree is a 2. This is an x squared. This is a parabolic function, a parabola, and it has a leading coefficient of -2. Therefore, I already know if a is equal to a -2, it's going to be a downward opening parabola. So I already know what this thing's going to look like, don't I? It's going to open as a bowl shape going down. I knew that from my first section, but that doesn't disagree with what we've done in this section. So I'm going to use the leading coefficient test to sort of prove that to myself. The leading coefficient of this one is, the degree of this one is a degree of 2, right? And of course that is an even degree, and the leading coefficient of it is -2, and that is a negative. So what do I expect? Well, I expect the tail end of my graph to go down, don't I? And since it's even, I expect both the beginning and the ends of my graph to do the same thing, and that ties into what we already know. It's going to be a parabola. It's going to look like this, okay? So your leading coefficient test agrees with what you learned in section 4.1, doesn't it? Let's look at the x-intercepts now. We want to look at the zeros of x, and to do that, we've got to factor this. So I'm going to say, well, 0 is going to equal to, and I really don't even have factorization for it as in my head at the moment, but I know I'm going to factor out that negative. And I'm going to say 2 times x squared minus 7x plus 5, and see where I can go with there. And if I can factor it, let's do that. Let's don't go straight to the quadratic formula, because that one's kind of difficult. But I'd look over at my old factoring techniques and see if I can use them. I say, well, this is the a term and the c term, and I would put in my diamond using the diamond method. I'd say 2 times 5 gives me 10, and then my b term right here is a -7. So I'm using this diamond to sort of say, okay, can I quickly find these factors? And I always write the coefficient of x and x here. The coefficient goes with both of them. And I know that these have to be, because this second operation here is positive, it has to match the first operation. So if this factors, they'll both be 2 negatives, won't they? They'll have x coefficients, and they'll have something in front of them probably. So what am I looking for? Well, I'm looking for factors of 10 that combine, that add together, right, to give me a -7. Well, what if I had factors of 10 that were -5 and -2? I see that would easily work, wouldn't it? So I look at my first one and I say, well, that's going to be 2x minus 5. That's my first factor. My second one is not going to be 2x minus 2. I will reduce those, acting like they're fractions. I'll have x minus 1. Now check it. 2x times x is 2x squared. -5 times -1 is +5. And if I multiply these inside terms, I get -5x. Outside, I get -2x. That combines to give me my -7x, so I easily factored it, pulling out the negative first, right? So what do I have as far as the zeros here? Well, the first one is this -1, isn't it? So it would say 0 is equal to a -1, which is never true, so I don't have to even worry about that. Then I say 2x minus 5 would equal 0, and I'll set the other one, x minus 1 would equal 0, and I'll solve this. 2x would equal +5, and x would equal, and here's where I don't like it, because I end up with 5/2, don't I? This one, of course, is a little bit easier. X is equal to a +1. Now, these are my zeros of x's, and they each happen one time. I'm going to write under here multiplicity of 1. And this one also has a multiplicity of 1. And so what they're going to do is at the x-axis, they're going to cross. They're not going to turn. They're going to cross at that point. All right, what point is that, though? Well, it's where x is 5/2. Now that is going to be 2 1/2, isn't it? 2 1/2, or right about here is where I expect it to cross. And I also expect it to cross where x is equal to 1, right about here. Now, the only other thing, I know it's going down, and I know this one is going down. The only other thing is I've got to see is how far up does it go? And I kind of want to look at that axis of symmetry if I can and find out where it is. And what I do is I see if I can remember what I did in the first section. So next, let's see if we can find, let's just go ahead and see if we can find the y-intercept. That's part C that they asked us to find. And I go back to my original equation up here, and I say that's where x is equal to 0. What is y if x is equal to 0? Would that be negative 2 times 0 squared plus 7 times 0 minus 5? And this, of course, is going to be 0. And this term is also going to be 0. So y is going to equal a negative 5. Now I know something else. I know it's going to cross the y-axis right here at negative 5. Now that tells me a lot about it, doesn't it? It's going to take this point and it's going to turn and go down. I know the ending of it goes down on this side. I know the beginning of it goes down. I just don't know where it turns around. Isn't that, though, because it's a parabola, isn't that going to be the vertex point? So I'm going to look for the vertex just to give me that point. So I'm going to, because it said, if necessary, see, a few other points. Well, I'm going to look for the vertex because I know how to do the vertex of a parabola. I go back to my original equation and I say x is going to equal negative b, which would be a negative 7, over 2 times a, which is a negative 2. Well, that's going to give me negative 7 divided by a negative 4, which is, of course, 7/4. Once again, I've got fractions that I don't really like, but I can live with that one. So next, x is going to equal 7/4. Now, the next thing I've got to do is say, what is y if x is 7/4? And this is kind of a maybe math that you have chosen to forget, but you need to kind of remember. So let's do it together here. I'm going to say, well, y would equal, back to the original equation, negative 2 times, and I'll say 7/4 squared. And then I can say plus 7 times 7/4 minus 5. All right, so what is y going to equal? Well, I'm going to say that's going to be negative 2 times 49 over 16 plus, and I would multiply 7 times 7 and get 49 over 4. And then I'm going to subtract 5. Now, at this point, I'm going to reduce this particular fraction. I'm going to say, I can say negative 2 will reduce with that 16, won't it? And I would end up with over 8. Would that help me a lot? Well, I don't know. Maybe I can just multiply everything through by 16 and clear the fractions. Why don't we do that? You remember how that works? I'll say 16 times every term. So I say 16 times y. And then when I multiply this one, I say times 16 over 1, right? And it will reduce these fractions. But this negative 2 would still be there to be multiplied times 49. I know you can do this with a calculator and end up with decimals, but you do need to know how to do this math. And this is going to be times 16, right? Which is going to mean I'm going to reduce it and multiply that times 4. So I'll say it's times 4 times 49. And then I'm going to say minus 5 times 16. Everything has to be multiplied times 16. All right, I've gotten rid of the fractions though, haven't I? So 16y, I can quickly do this math now, is negative 2 times 49, or negative 98. And then I say 4 times 49 gives me 196. And I say negative 5 times 16 is at negative 80. Well, that's easy to add those together. 16y is going to equal, when I finish adding these and subtracting those, or taking 196 and subtracting 80 and subtracting 198 from it, I get 18. So what do I have now? Well, now I still have to divide. Y is going to be 18 divided by 16, which I can reduce. I'll divide both of those by 3, and I get, by 2, and I get 9 over 8. And so that's what y is going to equal. So if x is 7/4, y is 9/8. Now, I've chosen to do it as fractions. You can use your calculator and do it as decimals, but sometimes this is good math to have in your back pocket. So what is my vertex? Well, it's going to be, and I'll put it vertex here, is going to be 7/4, 9/8. So I can graph that because 7/4 is not quite 2, it's 1 3/4, isn't it? And I'll go, in the x direction, I'll go 1 3/4. I'm going to come right about here with it. And then I'm going to say, 9/8 is just a little above 2. So it's going to end up being right about here, somewhere in there. Really close, isn't it? Now, I know that it will turn around there and go back through this point and keep on going until it goes down. And that is a really good graph. But let's check this graph and say, does it have y-axis symmetry, origin symmetry, or neither? Now, if it has y-axis symmetry, we could fold this on the y-axis and both sides would be exactly the same. But you can tell if I fold this on the y-axis that they don't match. This side of my graph does not match this one, so it doesn't have y-axis symmetry. If it had origin symmetry, then opposite or opposing quadrants would be the same. If I fold it, this quadrant does not match this one, and this one does not match that one, so it doesn't have origin symmetry. So what it has is, for symmetry, this one is neither. And that was question D. I'm going to say symmetry, neither. And we've done our graph by checking and putting a few little extra points in there, and we did that especially by finding that vertex of our parabola. So that would be the end of that problem for you. But I do want to mention one thing about this one, because it does come out with these points that look like they're in fourths, is what it looks like to me. And if you choose to check this with your TI-84 calculator, you can do it, or 83 or something, but you're going to need to use second table set. I think it's table set. And you're going to need to set it to, you're going to need to reset it to fourths. You're going to need to be increments of fourths or 0.25, right? I'll say fourths. You're going to need them to be in increments of 0.25. And that's the only way it's really going to show up. Otherwise, you're going to end up with whole numbers. It's going to look like whole numbers, but they're not going to be completely accurate representations. Let's do another problem and see if on page 12, see if we can answer some of the same questions and graph this one. So the first thing we're looking at with this particular graph is, what is the leading coefficient? Our leading coefficient test was the first question that they asked us. So I'm going to look at these x values, and I know they're multiplied times each other, and I have to look at what their exponents are because they're going to be added. So this is x to the power of 1 times, and this one would be x to the power of 2, and this one would be x to the power of 3. I know I would add those exponents, and I would get an exponent of 6. So I'm looking at this saying my degree for this particular polynomial function is going to be 6, which is an even degree. And then my leading coefficient is really just going to be a 1, because no matter what I do, when I finish multiplying them out, I don't have any numbers in front. This is just going to be multiplied. It's just going to be 1. So that's going to be odd, or positive is what I meant to say. It's positive. So since it is positive, I know the end of my graph is going to, the tail end is going to go up. Since it's even, I know that both of them are going to have the same direction to them. So I'm looking at it being both pointing in the upwards direction. And since I'm looking at a degree of 6, I'm expecting this thing to change direction quite a few times as it goes through. Now, it can change directions. It can have 6 different directions. It could really have 4 different directions. It can do a lot of different things. So I'm going to probably use my graphing calculator to determine that a little better. Let's look at the rest of it and see if we can see what the next question was. What are the zeros of x? Well, it's already factored for us. So I can say that 0 would equal x times x minus 1 squared times x plus 2 cubed, right? And I know if any of those were 0, that it would make my statement true. So the first one is x is equal to 0. That is a multiplicity of 1. So I expect it at 0 to actually, where x is 0, to actually cross the x-axis, don't I? And then I'm looking at the second one, and I'm going to say x minus 1 is equal to 0. So x would equal a positive 1, also a multiplicity of 1. So I'm expecting it to cross at x is equal to 1. And then the third one, I would say, is x plus 2 is equal to 0. X, of course, would equal a negative 2. It has a multiplicity of 3. And since that's an odd multiplicity, I expect it to touch and turn. So here it's going to cross. Here it's going to cross. And where x is equal to a 2, negative 2, sorry, it's going to touch and turn. And let's reverse all of what I just said. Go back with me just a minute, because you see x minus 1 has a multiplicity of 2, doesn't it? Instead of the crossing, I'm going to expect it to turn at this point, which was what I was thinking when I wrote that. With this odd multiplicity, of course, I expected at a multiplicity of negative 2 to cross. Hope I didn't confuse you with that. Okay, if I have odd multiplicities, I expect it to cross. I have an even multiplicity, I expect it to turn around. And of course, we look at the exponents and see how many times is that factor repeated. This one's repeated twice, multiplicity of 2. This one's repeated 3 times. Of course, that's a multiplicity of 3. So I know a lot about this graph. And I can sort of tell, what it's going to do at the ends. And let's see what else I can figure out about it. First, I'm going to look for the zeros. And those I can go ahead and graph. So I'm going to say x is equal to 0 is right here. I know it's going to cross at that point. X is equal to a 1 is where I'm expecting it to turn, but I'm going to go ahead and put that in there so I know what I'm doing. And then I've got another one, don't I? I've got x is equal to negative 2. So those are my 3 zeros that I found. Now, another thing that would be useful to me is to find the y-intercept. So I'm going to say y is equal to the whatever y is equal to when x is equal to 0. So I would say 0 times 0 minus 1 squared times 0 plus 2 cubed. Well, 0 times any of this, and 0 is multiplied times both of these, I can't get anything but 0, can I? So where is that y-intercept? It's actually crossing the y-axis right there. Same intercept, and I should have known that, right? Because that's the one point it's touching, that y-axis. So anyway, my y-intercept is confirmed. It's y is equal to 0. Now, I'll plot it, and then I'll see what kind of symmetry it has, but I'm going to need a few more points in it. I know it's going to have come down this way, and then I know it's going to turn around and do something before it turns around and comes back down and touches this and turns. But I really don't know what this graph looks like, and I need to use my graphing calculator at this point to see. So I'm going to go to y is equal to, and I'm entering the original function into that calculator, x times x minus 1 squared times x plus 2 cubed. And then I'll take it and look at my graph and see what it looks like. Now, I don't know if you need to adjust your windows, but I've kind of got my x and y's the way we usually have it set. And it looks like it comes down and it kind of touches and flattens at x is equal to negative 2. And it turns and goes down to a point here somewhere before it turns around, comes back up and turns around. I really need to identify these 2 points. And I can try to identify them with this particular minimum and maximum, but it might not be completely accurate. Let me just see if I can find some points on the graph that kind of agree with what I've got here. I need to know what this point is. It looks like it's going to be where x is negative 1, and I'm going to try and plot it myself or try and calculate it myself and just see what I come up with. In case I come up with fractions and my table needs to be reset is my problem here, okay? So when I say x is equal to negative 1, what is y? And that calculation's not really that hard for me. Y would equal negative 1 times negative 1 minus 1 squared times negative 1 plus 2 cubed. And that's going to be negative 1 times, let's see, this is going to give me negative 2 squared, right? and that's going to be times 1 cubed. And here I'm going to have negative 1 times, that'll be a positive 4, and it'll be multiplied to 1 cubed. It's just 1. So what's it going to be? It's going to be negative 4. And those look like whole numbers, and that looks like where I've got x is negative 1, y is going to be negative 4, and that looks like the turning point of that graph to me, or very, very close to it, doesn't it? Close enough that I could say that's probably what I'm going to graph that. Now, if I wanted to find out more about it, I would check the minimum. I'm going to say second and calc, and I'm going to go looking for the minimum. And at this point, I have to move a little bit to the left of the minimum. It's asking for the left bound, and I put my cursor left of it, and I hit enter, and it draws a line, and then I move my cursor right of it, and it says right bound, and yeah, that's to the right of it, and this says guess, and I'm going to move my cursor back to the center because that's what point I want it to guess is the middle of it. And when I say guess, it gives me a minimum that's of x of negative 7.6 and a y of 4.48. So when x is negative 7.6, y is a little bit south of this is what it is, probably in here. So I know it goes through this point, but it goes through this point and turns at this one, doesn't it? And comes back and goes through the x-axis, hard to draw that. And then at some point up here, it's going to turn around. To me, that looks about where y is equal to 0.5. X is equal to 0.5. Well, I can check that with the maximum of my graph. I'll go second and calc, and I'll go looking for maximum. And I'm going to go put it right here and say, okay, it's to the left of the maximum that I'm interested in. And then I move it over and say, and now I'm to the right of the maximum. That's the right bound. And then I move back and say, that's the point I'm interested in. And I hit enter and say guess. And it looks like it's going to be where x is 0.43, y is going to equal 2. That's close to what it's saying for this particular graph. And I could calculate it, and I could do some calculations with it. I would kind of guess where x is 0.5, and if you wanted to, you could plug in an x of that's right, 0.5. That's a decimal. If I plugged in x of 0.5 and did the math for it, I would come up, should come up with a 1.95, almost 2, okay? So 0.5, 1.95 is going to be right up here somewhere. I know that's going to be where it's going to turn. I've already kind of seen with my graph. And it goes back through here, and at some point it just keeps on going down. Oops, I'm sorry. It touches and turns at that point and goes up, right? Ignore that. And at this point, this side has to just keep on going up too. So this is what my graph looked like in the graphing calculator. I don't have the little flattened part quite as well. But then it turns and goes back up, and I can graph it fairly accurately using my calculator and using what I know about the graph. There is a lot in this section, but as you're doing your My Open Math homework, you're going to find there's some really good intro videos and some videos to help you through it, especially the video that one of my colleagues has put at the beginning of the section. If this doesn't help you with the homework problems, that particular video at the beginning of 4.2 will.